Okay, now that we've looked at scatter plots, how to describe them, a little bit about the relationships, we're going to move into how to analyze these using statistics and specifically the calculations in Excel. So we won't be doing any calculations by hand, but I will go through the formulas so you get a sense of where they come from, and then we'll be using Excel to do all of this. So we're going to start with the correlation coefficient, and that's represented by the lowercase letter r. And that correlation coefficient is a number that measures the strength and direction of the linear relationship between two quantitative variables. So it gives you the direction in terms of if R is positive, then the relationship is positive and it's going uphill. If R is negative, then the relationship is going to go downhill. So you get a negative relationship. All right, so before you can use this process, there's a couple of things you have to take into account. So the first one is you do need to make sure that you actually have two quantitative variables. So you have numerical data with units, otherwise this process doesn't apply. You do want to make sure that it does look mostly pretty linear. So this is a little bit of a judgment call, but it should be fairly clear that it's linear in order to use the correlation coefficient. And then the last one is the outlier. So you do want to be really cognizant of outliers because they can do one of two different things. An outlier can take a strong relationship and really make it look weak, but it can also do the opposite. So if the relationship is weak and you put an outlier in the right spots, then it can actually make the relationship look stronger than it is. So whenever we do correlation coefficients and scatter plots, we kind of do it both ways, where we look at it with the outlier and without the outlier. We generally report both of those just to give a really complete picture. All right, so we're going to take a look at this formula, and it is a little bit gnarly. We will not do it by hand, and this is all pretty much written in your notes. So I think you can just follow along for the next slide or two. So that correlation coefficient is a number that's going to indicate the direction and strength. And so we want that number to remain constant no matter what units are used. So if I switch from miles per gallon to feet per second, I want this to still have the same value and still mean the same thing. So to do that, we have to standardize each variable. So here's how this works. We have two variables. We have the explanatory variable on the x-axis and the response variable on the y-axis. You're going to need the mean and the standard deviation for both of those variables. And then what you're going to do is you're going to take each point in your scatter plot and you'll take the x value and subtract off the average and divide by the standard deviation for x. And then you'll take the y value for that point. You'll subtract off the average for y and divide by the standard deviation of y. And then you're going to put it all together in this crazy formula where you multiply things together and you divide by n minus 1. So that n minus 1 that you see in that formula maybe seems a little bit weird. We know n is the sample size, the number of points we have. N minus 1 in statistics is known as the degrees of freedom. And it's a little bit of a correction factor, and we're going to learn more about that kind of towards the end of the semester. So for right now, if you know that n minus 1 is the degrees of freedom, that's fantastic. But otherwise, we are going to talk about that again later in the class. All right, so let me give you an example so you can actually see this with real numbers. And this is also in your notes. So I don't think you need to write anything down for that as well. So here we have the age of 7 people and the amount of text messages they sent in maybe an hour. That probably seems about right. And so I went through and I found the mean for the age and the standard deviation. And then I took the second column with the text messages and I did the mean and standard deviation for that. So I'm going to take that first point, the 16 and the 21, and I'll run through the formula with you. So to standardize it, I'm going to take that 16 as my x value. I'll subtract the mean for the age and divide by the standard deviation. And that gives me negative 0.88. And then same deal, I'll do it with the y. So the y value here is 21, and I'll subtract off the average for text messages and divide by the standard deviation text messages. And I'll do that for each and every point in my data set. And then I'll multiply each set of x and y together and add them all up. And then I'll divide by 6, so 7 minus 1, because I have a sample size of 7. So this gives me a number, negative 0.95. So it's negative, which means I know that it's going downhill. So that's helpful. And then in the next slide, we'll look at what that 95 actually means. Before I do that, I did promise you that you're not going to calculate this by hand. So let me give you the formula for Excel. And there should be a spot in your notes in a box to write that. So that formula is equals CORREL, so for the correlation coefficient. And then you have to highlight two separate things. You're going to highlight one column, you'll put a comma, and then you're going to highlight the other column. It doesn't matter which order you highlight the columns in, but you have to highlight them separately. Okay, then when you hit enter or return, that'll give you this negative 0.95 that I got. Right, so that is how you'll be finding the correlation coefficient in this hand, never by hand, never with this formula. Okay, so let's look at what this 0.95 means. All right, so I have actually a bunch of scatter plots here. This one at the top is 0.9, then negative 0.8, 0.7, all the way down to a 0.1. So the values of R can be negative or positive, but they're stuck between -1 and +1. Okay, so you can't have R equals 2.8. That's not a thing. So the biggest it can be is -1 and +1. So now let's kind of take these numbers and match those descriptors of strong, moderate, and weak kind of to these. So it's strong if the data is tightly clustered. And in general, that's a number that's closer to like negative 0.75 on the downhill side or positive 0.75 on the uphill side. So that's kind of these ones in the top. If it's moderate, there's some spread. You can definitely still tell it's either uphill or downhill, but maybe it's a little bit harder to kind of fit that line in there. So I would call that moderate if the number is closer to negative 0.5 or positive 0.5. So it's kind of this middle row of pictures. Then this bottom row of pictures, we would call weak. So if it's close to negative 0.3 or positive 0.3, it's spread out. There's still sort of a general direction, but it's getting really difficult to figure out exactly where to put that line of best fit in there, just to get a sense of how those things fit. And then none, which means it's like completely scattered. You let my nieces and nephews have a jar of glitter and they threw it everywhere. So completely scattered, you're really not even sure if it's uphill or downhill. That's going to be really close to 0. So closest to 0 is going to be just nothing going on, or there's something else that could be going on. But if there's no pattern at all, you're going to get a correlation coefficient of 0. If it's perfectly lined up, so all of those dots are in an exact line. If they're going uphill, it'll be R is +1. And if it's a perfect line going downhill, we'd say R is equal to -1. And so I generally draw a line through there just to kind of see how the dots fit around that line. I mean, in chapter 5, we'll do a lot more with that line, but for now, it's just a good way of getting a sense of how spread out your data is.